time we had talked about 1.1 and the start of 1.2, right? I think we had said you guys could probably do like up through 4 from the problem set. Does anybody have any questions on anything that they might have seen to that point?
Could you do number 3?
Sure. Now come now. All right, so we have, do the following relations represent y as a function of x? And then explain your reasoning. So what this means is that this is my independent variable, and this is my dependent variable, right? So, one way I could do this is I could pick a value for x and see if I can get more than one value for y. So maybe we say, let x equal 2. So if I solve this for y, divide both sides by 2, I square root both sides, and I get 2 y's. So I would say no, it's not a function because x equals 2 goes to y equals 1 and to y equals negative 1. That's an explanation. That's reasonable. You could have said, I'm going to rearrange this to get the y by itself. So divide both sides by 2. Square root both sides. In doing so, that generates a plus or minus. You could have observed there that the plus or minus is going to indicate you that this will fail a vertical line test. Or you could have gone ahead and graphed this thing on your calculator at that point. Now to graph this, you would need 2 equations. So one for the positive version, and then one for the negative version. And then you could state that that fails a vertical line test after you provided a sketch. So any of those ways of going about that would be fine. Doesn't really matter to me. All of them, I think, are perfectly valid explanations. Does that feel okay?
Yeah.
Okay. Cool. Anybody else? Cool. Let's pick up where we left off from last time then. So we'll finish out 1.2 and should be able to do 1.3 after that. So in 1.2, we had talked last time about interval notations and went through a bunch of different sets and wrote out their interval notations based on the set description. You guys remember doing that? Or at least recognize that that's what we did last time. Maybe if you don't remember specifically what we did, but like, okay, yeah, that sounds right. What we're going to do now is start talking about how we come up with the domain for a function. What is the domain? It's the set of inputs that have an output paired to it. Everybody's okay with that idea? So if we're given an equation, what's it going to look like if a domain doesn't have an output paired to it? What kind of result am I going to get? Braden? Undefined. Yeah, that's exactly right. So what I'm going to be searching for are values of x that make my function undefined, because those things are going to be what I don't want in my domain. Now, to this point, we've seen 3 operations that can give you a result that's undefined. Does anybody remember any of these 3 operations? Braden. Yep. So division will do it. Great. That's an oldie, right? That's like a pre-algebra idea. But you dealt with it last year when you dealt with rational functions as well, right? What else? The other 2 are both distinctly Algebra 2 topics. Yeah, Katie. Square roots of what kind of numbers? Yeah. Good job. Everybody's cool with that? And there's one more. What's the fuzziest topic from Algebra 2 in general for you guys? You don't know? It's got to be logs, right? Everybody's like, yeah, we did it. I don't really know what I did, though. That's the other one. So logs can also create something undefined. So the log of a non-positive is going to be undefined as well. So you notice that I've used 2 different terms here. I've used negatives and non-positives. Is there a difference between those 2? Or are they synonyms? Braden? Yes, they are different. They differ by 1 number. Non-positives include 0 as well. Negatives do not. So you cannot take the log of 0 as well as the log of a negative. Everybody's cool? Okay, so ostensibly, these are the tools I'm going to use to algebraically determine a domain. I'm going to just look for if there's any division, square roots, or logs. And if there is, I'm going to take the part that I'm dividing by and say that can't equal 0. And find the part that's under the radical and say that can't be negative. And say the part under the log can't be non-positive. Okay? And then we'll figure it out from there. Let's do some examples. Okay. So I'm going to ask myself, do I see any division in this? No. Do I see a radical? Yes. So I'm going to stop and say, okay, all the stuff under the radical cannot be negative. That's the equivalent of saying it has to be greater than or equal to 0. Everybody's okay with that? Now I'm going to return to my function and go, are there any logs? No. Okay, so the only part I have to worry about is this radical piece. Everybody happy? So to solve this inequality, I'm just going to add both sides by 4. I don't know if that was real English there, what I just said. Add both sides by 4. I don't know. I'm going to go ahead and turn that inequality into something on the number line. So because it greater than or equal to 4 includes 4, I'll use a filled circle. And then my arrow will go to the right. If I want to translate this into interval notation, I would say bracket 4, comma, positive infinity with a parenthesis. Remember the brackets we use when things are included, when we use the filled circle. It's when we have the greater than or equal to or less than or equal to. And then to indicate that this is a domain and not just like some other set, I'm going to say X is a member of that set. Is that okay with you guys? Yeah, so it's like it's this symbol. It kind of looks like an E, but it's supposed to be like all curve. It's more like a C with a line in the middle. Yeah, kind of like the euro symbol. Sure. That's not what that symbol is. It's hard to write by hand. Mr. Kulik would not be picky about it if your symbol looks a little weird. Okay. Let's do another example. You guys feel okay on that? Fairly straightforward, right? G of x equals 3x over x plus 2. So, back to the beginning. Do I see any division? Yes. Where's the division? It's the fraction, right? Yeah, exactly. So I have to say, okay, my denominator cannot equal 0. Cool. I subtract 2 from both sides. And then I'll translate this to the number line. Remember to do a not equals to, that's going to be an open circle at the number, and then you have arrows pointing to the left and to the right. Everybody remember that? We did an example like this yesterday, I think. Okay. Translating this to interval notation, then I have negative infinity to negative 2. Both of those get parentheses because the infinities always do, and the negative 2 had the open circle at it. And then I do that union symbol, and then go negative 2 to positive infinity. Again, both getting parentheses for the same reason as before. And lastly, I would just make sure I wrote X as a member of that set to just make sure that it was clear to the reader that that set is the domain and not just some other set. How are you guys feeling? So far, so good? Go ahead, Katie.
Do you only write the X symbol?
No, you could do it if it's another set of X values. So if you're talking about like where the graph is increasing or decreasing, you might say that as well. But this problem is asking for a domain, so I don't know. But this helps clarity's sake. But you could do it other places. If the sets are X coordinates, you would put that in front. Okay. So what we've looked at right here, these two examples, these are something called implied domains. Because to calculate those, all of it just depended on the equation, right? Okay, so an implied domain depends only on an equation. There's also something called a relevant domain that depends on the equation and the context of the variables. So let's look at an example of that. So here the variables have some meaning, right? They're just not x's and y's or f of x's or x's and f of x's. Here, they're mean volumes and side lengths, right? They have some real world meaning. There's some context to the problem. Okay? So to do an implied domain, we're going to want to consider the equation part. So if I look at my equation, is there division? Is there radicals? Is there logs? So what does that mean? It's all real numbers. Everything you should be able to, if I'm looking only at the equation, there's no reason I couldn't plug anything into that. Now, if I look at the context, which variable is the domain corresponding to here? Oops, I should have wrote that as not x though, right? S is my independent variable in this problem. So S is representing my domain. Everybody's okay with that? What does S represent in this problem? No, like the context of it. Side lengths of a cube. Okay? What kind of numbers is it okay to have to be a side length of a cube? Positive. Everybody's okay with that? Now, if you had said non-negative, I think I would still count that, because I think it's just like depending on how the problem was set up, whether you, not this problem, but like you created this model to represent the volume of a cube, it would depend on whether you wanted to consider like a nothing still a cube, right? If you have side length 0 that has 0 volume, should that still count in your, with what you're going to use this model to do? I don't know, depends on, I guess. So if you wrote that as greater than or equal to, that would be okay in this context. I don't think it's clear at all which one it has to be, one or the other. You know what I mean? Okay. So anyways, we do this, and we got our 0. You know, I have open circle going to the right. So we have 0 to positive infinity. Everybody's okay with that? Yes.
So for 0 positive infinity, are you still going to continue in the previous question?
So this is, I'm just doing the relevant domain for this. We haven't finished yet.
Oh, okay.
Okay, so we need to consider the equation piece and the context piece. So that's what we've done, right? We have the equation and then the context, and then we're going to put these together. So from the equation, we have all real numbers. From the context, we have all the positives. My relevant domain is going to be the overlap of these two, which is convenient in this case because the overlap of these two is going to be the same as the domain from the context, right? If you take everything and you overlap it with anything, it's just like the overlap is whatever the other thing was. You know what I mean? So that would be our final answer. Is that okay with what we did there? Just from a fancy set perspective, when we looked at the overlap of these two sets, that has a name that's called the intersection. Not that that matters, but if you're like a names person, that's what that is. What do you guys think? Pretty easy, right? Not a big deal. The last one's the only thing that's kind of tricky because you have to like think about like in the real world, does that, you know, if the variable has to be, or the variable is representing this quantity, does that mean that like certain values are nonsensical, right? But in general, like, it's just some pretty easy algebras. Okay. Now we need to talk about the range. Finding ranges algebraically. Now, I fully acknowledge that most of us are pretty comfortable looking at the calculator at the graph of the function and pulling a range from the graph, right? I think you do that pretty frequently in Algebra 2. You look at a picture of the graph and pull a range from it. I want to talk about how we would do this algebraically, because depending on the directions, I might ask you to do it, just find the range, in which case looking at the graph is fine. Or I might ask you to find the range algebraically, which I'd expect you to kind of do this kind of a process. I know. It'll be okay. Everybody's on board, kind of understand the context or the directions thing going on? Okay. Because what's the catch about finding the range just by looking at the picture? Are you sure? Probably not. It's probably just a really good guess. You know what I mean? Doing it algebraically, are you sure? Yes, we will be sure. So that's the advantage here. Now it's more complicated to do it algebraically, because looking at the picture is pretty easy. It's just like low point to high point for each of the connected pieces. Not so bad. Algebraically, it can be a little bit more complicated. All right. So let's just kind of work through some examples here, and we'll kind of talk about what's going on. And I'm going to use the same functions that we had looked at previously. And I'm also going to use the answers to our domains. Okay, so I'm going to assume that I have the domain as well from our previous answers. Everybody okay with that? So what I want to do is I want to look at the original function and find out where it's increasing and where it's decreasing. Everybody's okay with that? What's going to be the easiest way to tell where it's increasing or decreasing? Look at the graph, right? What does the graph of something that's increasing look like? Like if you walked along the graph, you should be walking uphill from left to right. If you walk from left to right and you're going downhill, that means it's decreasing, right? And could a graph be both increasing some places and decreasing some places? Sure. Well, that's kind of the worst case scenario where you have to kind of pick apart what's going on there. But I'm just going to take a look at this first function really quick, and what do you notice? It's increasing everywhere, right? Everybody agree with that? So this one's increasing. And it's increasing everywhere. Well, when I say everywhere, I mean over the whole domain. But you guys get that, right? So since we are increasing, my range I can calculate in the following way. So it's going to be f of the lower bound from the domain, comma, f of the upper bound from the domain. And the brackets and parentheses go with this, are the same as from the domains, right? Since I'm using the lower bound from the domain, I'm going to use the same symbol from the lower bound of the domain. When I'm using the upper bound of the domain, I'm going to use the same symbol from the upper bound of the domain. Is everybody okay with that? Okay. So here, the lower bound is 4, so I'm just going to calculate f of 4. When I do that, I get 0. Is everybody okay with that? 2 times the square root of 4 minus 4. It's 0. Is that okay? When I do the upper bound, I'm doing f of positive infinity. Now here I have to be a little bit creative. If I take infinity and I subtract 4, what do I have? Infinity. If I take the square root of infinity, what do I have? Still infinity. If I do 2 times infinity, what do I have? Still infinity. Everybody's okay with that notion? And since, in addition, since I'm talking about the upper bound, I know that that infinity there has to be a positive infinity, because you can't ever have a negative infinity as your upper bound, because there's nothing bigger. That's not bigger than anything. It's smaller than everything. So it could never be in the right-hand spot of your interval anyways. Is that okay? So the next question would be, what if it was decreasing? Right? What would we have done if it was decreasing? Well, if you're decreasing, things would have flipped. So not that this was, but if it would have been decreasing, you would have flipped where you plugged in the input, or the lower bound and the upper bound. So if the function was decreasing, you start with the upper bound, f of the upper bound, and you end with f of the lower bound. Chanel. So when I plug 4 into f, I get 0. Is that okay? No problem. Is everybody okay with that idea? Let's look at the next one. Okay? Okay. So just like before, I'm going to start by looking at the graph. So I notice something very different is going on here, right? What do I notice that's different about this graph versus the previous one? There's like 2 pieces to it, right? So just like I have 2 pieces to my domain, I'm going to expect to have 2 pieces for my range, which is fine. If I look at the first piece, as I walk along the graph from left to right, that's increasing. Everybody agree? If I look at the second piece as I walk along the graph from left to right, also increasing. So this is increasing everywhere. Everybody okay with that? So I'm going to do that. So I'm going to do f of the lower bound, comma, f of the upper bound, union f of the lower bound, f of the upper bound, since it's increasing the whole way. Everybody cool? Right, like just taking these. Right? Is that cool? Okay. All right. So, okay. So let's do this first one. What is 3 times negative infinity? Oh, all right. We're gonna have to be a little bit careful here because we're gonna have 2 infinities in this. Does everybody see that? Rather than just infinity in numbers like we did for the previous one. So we have to be a little bit more careful. So I'm gonna write this one out. Everybody okay with that? Just plugging in. That's okay. No problem. You can ask. It's okay. All right, everybody's good? Let's do the denominator. Everybody's okay with that? What's 3 times negative infinity divided by negative infinity? 3. So in general, if I have more than 2 infinities or more than 1 infinity, I'm not mucking around with the multiplication until I've done all the addings, right? Is that, you guys see what I'm saying? Okay. If I do this, I got that. That's undefined, right? But as I divide by numbers closer and closer to 0, what's happening to the value of that fraction? Well, let's just illustrate numerically, right? So let's say I have negative 6 divided by 1. Then we'll do negative 6 divided by 0.5. And then negative 6 divided by 0.1. And then negative 6 divided by 0.01. What's happening here? Yeah, the number is shooting towards what value? Negative infinity. And if I'd come from the other side, if instead I started with like 6 divided by negative 1, and then gone down and tried 6 divided by negative 0.01, what is the value heading towards this way? Positive infinity. Everybody kind of see that? So since it could be either answer, right? Which answer do I want if this is the upper bound of my interval, though? The positive infinity. Okay, so if I have something divided by 0, I'm going to have either a positive or negative infinity, just whatever fits in the part of my interval, or in the part of my interval, yeah. So this, I know, is negative 6 divided by 0. We just did that already. Everybody agree? And here, since this is the start of my interval, I want to use negative infinity. Is that okay? When I have something divided by 0, you could have either answer. I'm positive infinity or negative infinity. I'm just going to pick the one that works for my interval. Because we always have to go from small number to bigger number. So you can't have the biggest number possible first or the smallest number possible last. Does that feel okay? And then this is going to be three times positive infinity over positive infinity, or just 3 again. So there we go. What do you think? Who is sitting there thinking, okay, Mr. Kulik, that's fine, but what about the ones that have both increasing and decreasing going on in the same time? Right? We haven't addressed that situation. I said that that can happen. We all agreed that that can happen. None of your examples that has happened in. Can we do an example where that happens? Sure, let's do that. Everybody okay? I am such good friends with my stylus. Ariana and Morgan, are we okay?
Yeah.
We look collectively distressed. Do you have some?
Yeah. We're not even administrating stuff. So.
It'll get better. I promise. I promise. The everything will start connecting together, and the pieces will start locking in, and it'll get easier. I shouldn't say easy. Some of us it's, but it just takes a little bit of time. Don't get frustrated. Don't give up on me. Keep asking questions. If you're not sure, stop me and ask for some more. That's okay to do. Okay? Tessa?
I don't know if it's like a stupid question. I don't know if this is clear. But you said you plug it in, like, where did the 2 go? I don't think I understand the step of like 2 versus.
So you're talking about going from here to here?
Yeah.
Negative infinity plus 2, still negative infinity. Right? Like you add or subtract to an infinity, it's still infinite. Right? Like infinity is massive, 2's nothing. Right? Even 10 million is nothing to infinity.
So you would add or subtract.
Yeah. Other than infinity, infinity plus infinity or infinity minus infinity, or infinity minus infinity is the one you have to be careful about. That's indeterminate. Like, that's not 0. I know. But we won't see that. You won't see that. I promise. When you do AP Calc, we'll talk about like what the indeterminate forms are and that kind of thing. But that's a year away. So don't lose a lot of sleep over that. This is really non-intuitive. All this stuff that happens at infinites is like kind of brain busting. And the reason it's so brain busting is because there's not just one kind of infinity. There's like different sizes of infinity. And you're like, what? Why would that be? And I don't want to like go off on a tangent here, but like it makes everything really kind of, it often violates your instincts. And it's like, this seems really unintuitive. Like before when I didn't want to do 3 times negative infinity is negative infinity because I had the infinity over the infinity and I was like, I need to deal with this separately kind of thing. It's hard. It's okay. Here's the good news. is like a tiny little piece. It's like a nothing burger of a section. So like, if this doesn't go well, this section doesn't go well, it's okay. It's like more complicated than it needs to be for such a little thing. Okay? So I'm telling you right now, like if it's bad, do the best you can with it. But this piece does not is not foundational to the next thing. Okay? I don't know if that makes you feel any better or not, but maybe a little. Okay, I don't know. I'm trying, guys. I'm trying. Let's do this. That's a good one. Let's do that. So right away, what's the domain for this got to be? This is an Algebra 2 thing. You should just be able to look at it and tell me. All real numbers. Very good. How could you tell? It's a quadratic, but more generally even it's a polynomial. The domain for every single polynomial is all real numbers, right? That was a result from Algebra 2. That's a nice one to hold on to. Okay? So, let's go ahead and take a look at the graph and see where this thing is increasing or decreasing or both or whatever. Well, it can't be both at the same time, but like where it's increasing and where it's decreasing. Okay, so if I look downhill, 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 and then uphill, 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 uphill. So we have a section of the graph that's increasing and a section of the graph that's decreasing. Everybody agree with that? So I'm going to split this domain into the part of the domain that's increasing and the part of the domain that's decreasing. Good luck. Get some hole-in-ones or something. Like that's not a big deal, right, as a golfer. I get like 3 a week. It's fine. That was do you remember, so Kim Jong-il was the old dictator of North Korea or whatever. And it said he'd like routinely get like multiple holes in one per round of golf. Like that was something he said in public, which is kind of a dubious claim there. Seems not real. Anyways, probably had people hiding in the woods that would take his ball out and throw it in the hole or something. All right. So if we look at this, where does this graph change from increasing to decreasing at? At -1. That's what it looks like in the picture, right? So we know that, oops, that's not right. And I'm going to use a bracket here. So you guys say -1. Other than like you read it from the graph, is there another way you could have found it? Well, x to 0 is going to find you the x-intercepts. That's just going to get you the y-intercept. Or the h of x to 0 is going to give you the x-intercepts. X to 0 is going to give you the y-intercept. Neither of those is this point. What is this point called? The vertex. We had an equation to find that last year in Algebra 2. Does anybody remember the equation to find the x-coordinate of the vertex? It's -b over 2a. Maybe that looks familiar. I'm not surprised nobody was able to pull that. That's you use it for a week and then you forget it. So that would be -4 over 2 times 2, which is indeed -1, exactly as it looked on the graph. Well, we have to be sure, right? What if it was like -3/4 or -0.9 or something? be unlikely you'd be able to tell the difference between that and -1 without actually computing it, just by looking at the picture. You know what I mean? All right. So this is equal to the domain, right? If I take the union of these two sets, that's the same thing as the whole domain. Agreed? You guys good with that? So what I'm going to do then is I'm going to do the range for this piece, because this is the increasing piece. We keep the same order. And then because this is the decreasing piece, we switch the order. Yes, decreasing switches. Because if you think about it, like, decreasing looks like this, correct? The lower bound of the x is going to be the upper bound for the y. Right? The smallest x coordinate has the biggest y coordinate attached to it. And similarly, the biggest x coordinate has the smallest y coordinate attached to it. That's why it flips. Does that makes sense, right? If you look at the picture intuitively, like, oh yeah, sure. Yeah. What's up, Tess? Oh, here? That's a mistake. Thank you. I really appreciate you nitpicking. That matters. Definitely matters. If you think I make a mistake, speak up. Half the time they're mistakes. And it matters. It sure as heck matters. Like, it's a silly mistake Mr. Kulik made, but like, you don't know it's silly, right? This is the first time you're doing this. If you think it's wrong, you should ask. You did absolutely the right thing. Okay. I'm not going to pretend like I was just testing you. Mr. Kulik just makes mistakes. It happens. Okay? I will admit them. That's a good time to catch it, though, before it's kept on going. And there's only one thing to change. So, okay. Everybody's happy? So far, so good? If I plug 1 in, I have 2 minus 4 plus 1. That's -1. When I plug the -1 in. Everybody agree? Okay, when I plug the positive infinity in, I get 2 infinity squared plus 4 infinity plus 1. Or I get 2 infinity squared minus 4 infinity plus 1. Everybody's okay with that? By just plugging the infinity in, or negative infinity in, respectively? The only part of this that matters is that part. Why is that the only part that matters? Why don't I care about anything else? Infinity squared is massively bigger than any other part of that. That's a different order of magnitude of infinity. So everything after it is just small potatoes. It's the same reason why infinity plus 2 is just infinity. Right? Like infinity squared plus infinity, or minus infinity, just the infinity squared is all that matters, just infinite still. Is that okay? I know it's not, but absolutely. You're welcome. Sure.
Is the second one supposed to be like -2?
No, because negative infinity times negative infinity is positive infinity squared. Right? The squared kills the negative signs. Morgan.
Is the second one supposed to be -4, or is it +4?
So when I plugged negative infinity in for x, the negative sign right? It's if I plugged -2 in, it would be like 4 times -2, so -8 or whatever. So yeah, the subtraction symbol is supposed to be there. It just doesn't matter.
Like, that would be like if you did like, never mind, I'm not. No.
The good news is, whatever sign you want to make that, it doesn't matter, because the only thing that matters is the infinity squared part being positive.
-2 negative?
Because if you square a negative, it becomes positive, right? Like -1 times -1 is +1. You multiply 2 negatives together, that's positive, right? So negative infinity squared is positive. Is that okay?
Okay.
You're good? Okay. What do you notice here about these two intervals? They're the same. Are we surprised by this? I don't think you should be, considering that you had a continuous function that we just found the range for. I'd expect the range to just be one interval. Now, who thinks this is a colossal pain in the tuchus for something that's like, I can look at the picture and pretty easily tell what the range is? That's a normal feeling. On a test or quiz, would I ask you to do something this complicated? No. No. It would look more like this example. Okay? It'll look like this one, where it's like, it's just doing one thing. There's only one part to the domain. Like, it won't be bonkers. Okay? So like, are you going to see hard stuff in the homework? Sure. If it's come test time or whatever, would I give you the hardest parts from the homework? No, I will not. Okay? Will there be hard stuff on the test still? Sure, but I'm going to pick the hardest things of the hardest stuff. I'm not doing that. You know what I mean? Like, we can test if you know how to do this with something fairly straightforward. I don't have to give you like the most complicated thing that takes like a half an hour to sift through. Like, that's stupid. That's me wasting your test time for something that doing this would be sufficient to show me that you know how to know what you're doing. You know what I mean? I just want to be honest. Like, you guys don't know me that well. What we're doing right now was just really complicated. I can see that we're frustrated. And that's okay. Like, it's okay to be frustrated. I'm just trying to put your minds at ease a little bit that, like, if you're thinking, I could not do that again, I would not ask you to do something at that level again. Okay? And again, the homework, all you got to do is try, right? If you make a mess out of it, it's okay. You know, you can ask questions. All I'm grading on is completeness. It's okay. Don't freak out. It's only day, what, third day of class? Day 3, 4, 3? Yeah, we got a long ways to go, guys. We'll get through it together. Yeah. All right. Let's put that to bed. Let's talk about continuity, and this will be a relief. Okay? What does it mean for a function to be continuous? Well, I would say not necessarily, because if I looked at, say, a rational function, like a simple rational function has a vertical and horizontal asymptote. So this goes on to infinity, but it's not continuous. Yes, sir? Yeah, basically, if you can draw the graph with one pencil stroke, that's continuous. Does it have to go on in both directions forever? No, man. Like, if it ends, has endpoints like that, that's still continuous. I drew it with one pencil stroke. Is everybody okay with that notion? So if it's not continuous, that means that it has some type of discontinuity there where the graph breaks. There are 3 types of discontinuities. 2 of the 3, I think that you guys talk about. The third one we'll mention here. What's one type of discontinuity? Look at the previous example.
Hyperbolas. Quadratics.
Look at the first that you are trying, and I appreciate that. That is okay. So look at that first graph. What's going on where the graph breaks? Asymptote. Specifically what kind? Vertical asymptote. So that is one type of discontinuity. We call that an infinite discontinuity. So that's a vertical asymptote. So for example, if you have like f of x equals 1 over x, well, I'll say 1 over x plus 1. There's your infinite discontinuity. Everybody's okay with that? Are vertical asymptotes easy to find? Yeah, you just set the reduced denominator equal to 0 and you solve. You know, it basically boils down to solving a polynomial. It's not bad. Well, I mean, it could be terrible, but it won't be bad. I mean, the polynomials you'll solve will be like quadratic or less, right? So not bad. The second type, also having to do with rational functions, is called a removable discontinuity. So an example would be, say we have f of x equals x squared minus 1 over x plus 1. So if I look at the graph of that, would look something like this. Notice the open circle on the graph. That's a hole in the graph. That's your removable discontinuity. When do those guys occur? When you can completely reduce a factor from the denominator in a rational function. So this piece is where the removable discontinuity gets created, is when you're able to completely reduce some factor from the denominator. Because really what I've written is not accurate. It's equal to that except at -1, where it's not equal to anything there. Do you remember kind of doing that in Algebra 2? This is good. I like seeing heads bobbing. Yes. The last one is the one that we haven't seen before, I'm guessing. This is called the jump discontinuity. Okay. So, to get a jump discontinuity, we have to use a piecewise defined function. Have you guys ever talked about piecewise functions? Okay, let's do it right now. So what a piecewise function is the function rule is different for different pieces of the domain. So let's start with, say, that as our piecewise function. So for x greater than 0, the graph is x plus 1. And for x less than 0, the graph is going to be x minus 1. Everybody's okay with that idea? So if I wanted to graph this thing, to graph the green part, how many points, or what type of function is x plus 1? It's linear, right? It's a line, yes? How many points do I need to graph a line? 2. Now, I have to be a little bit careful here because does this line go on forever in both directions? No. It stops at what value? 0. So, or I guess in this case it's starting at 0. So when I make my XY table, I got to use 0 as one of my values. Any other value from x greater than 0 is fine, so maybe I'll just pick 1. So I have the point 0, 1 and the point 1, 2. So that's that part of my graph. This part we're going to do in green. What point or what x value, again, linear function, need 2 x's. What x do I have to use? Still have to use 0. Right? Because the graph is ending at 0. And then any other x that's less than 0 would be fine. Maybe I'll do negative 1. Everybody's okay with how I generated that graph? See how the graph breaks? There's like a jump in the graph. That's my jump discontinuity. Is that okay? Now, what am I going to expect you guys to be able to do with this? Look at the picture and tell me what's going on. Tell me what type of discontinuity it is. How's that sound? Pretty doable? Yeah. That's sufficient for what we're doing in this course. Okay? That's 1, 3. That's a little better, right? We can handle that. Just a little bit of vocab, basically. That's all that was. 1.4 is about increasing and decreasing functions. And we already talked about this, right? Because we needed it to be able to do the ranges algebraically. So increasing is where basically we're going uphill. Decreasing is where we're going downhill. There's one other thing that the graph could be doing, though. What's the third thing? Yeah. So there's like increasing. And there's decreasing. And then if you're not doing anything, what's this called? That's constant. Because what's the graph of like y equals 2 look like? Straight line, right? Straight horizontal line. That's a constant function. Horizontal part of the graph is a constant. It's part of the, just it's flat, has one value, just stays at that same value. Okay with that? So if I say, excuse me. Say we have this here. and I want to write down the intervals of increasing, decreasing, and constant. How many increasing intervals do we see? I see one, right? You guys agree with that? It's the only place where we're walking uphill. What x value does that begin at? Negative infinity. And what x value do we end at? Negative 1. Intervals of increasing, decreasing, and constant always get parentheses at both ends, because the strict definition is I can pick a point and then a point to the right of it, and it would have like positive slope for increasing. Can I pick a point to the right of the endpoint? No. So it always has a parenthesis at the end. Does that make sense? How about decreasing? Where is this? How many decreasing intervals do you see? 1. Where is it at? 2 to positive infinity, right? How many constant intervals do you see? 1. Where does it go from? Negative 1 to positive 2. Again, always x coordinates when we're describing our intervals of increasing, decreasing, and constant. Holden.
Oh, so that goes down.
Sure. What do you guys think? It's just looking at the graph and describing what you're seeing, basically, right? Is there any complicated algebra or anything going on here? Just kind of using some definitions and interval notation. Not bad. All right. So associated with intervals of increasing and decreasing, so let's say we have something like this. Notice that here the graph is increasing, and then it changes to decreasing. This point where we change from increasing to decreasing has a special name. What is this point called? It's a maximum. Everybody's happy with that? How many types of maximums are there? There's 2. You have local, and then you have global. The global maximum is the overall highest point. Does this graph have a global maximum? Assume we have arrows at the end. No. Why not? Because it's got an arrow pointing up, right? Any point you pick on the graph, I can find a point higher than that just by going a little bit to the right. No global maximum in this graph. However, this guy is a local maximum, because if I just look at its neighborhood, like look at this little part of it, it's the highest point in that part. On some open interval, it's the highest point. Everybody's cool with that? What do you think a minimum is? Yes, exactly. Where it changes from decreasing to increasing. And again, how many types of minima are there? 2, local and global. The one that we've drawn here, is that local or global? Local. Why? Got the arrow pointing down. There's always going to be a point lower just by going a little bit further to the left. There is no overall lowest point in the graph. How do you guys feel about that? finding these maxima and minima, what we call extreme points, is that going to be something that's easy to do or hard to do? So either maximums or minimums are called extrema. So you say it's easy. Okay. Well, let's do it then for f of x equals x to the fourth plus 2x cubed minus 4x squared minus 3x plus 1. How are we going to go about doing that? I'm going to use my calculator and the maximum minimum commands on my calculator. Yeah, you're right. That is what to do, is to graph it on our calculator. Anybody remember from Algebra 2 how many extrema this can possibly have? The answer is 3. 1 less than the degree. The reason is an extrema has to, or can only occur in between zeros, right? Like you have to, or at most you can have 1 extrema between zeros. Whatever. Anyways, it's 1 less than the number of zeros. Imaginary count. So if I look at this, I see a global minimum, a local maximum, and a local minimum. Everybody agree with that? To find the exact coordinates for these points, I'm going to be using the calculator's minimum and maximum commands. To locate the minimum and maximum commands, I'm going to press second and then the trace command. This opens the calculate menu. The minimum maximum command are right here. I'm going to find one of these minimums just to show you how the commands work. The two commands work exactly the same. Both commands are going to ask for 3 inputs. So at the bottom, you notice your calculator says left bound with a question mark. So let's say we're looking for the global minimum. To give the calculator a left bound, I have to move my cursor, which is right here, somewhere to the left of the max, or that minimum. So I'm just going to press the left arrow until I'm somewhere over on the left side of it, and then I'll press enter. It then asks for a right bound, so I just have to move it somewhere on the right side of it. So that looks good. I'll press enter, and then it asks for a guess. The guess doesn't matter as long as there's only one extrema in between your left bound and your right bound, which is the way I've done that. So I'll just press enter. So my global minimum is the point negative 2.242682, comma, negative 9.653029. That's it. Easy, right? Just using your calculator. Did you do this, use these functions last year? Excellent. You remember how to do it with a little refresher there? Excellent. In general, should I report all the decimal points from my calculator? Unless otherwise instructed to round to a certain number of decimal points, you should. If I ask for if I just ask for the max and min, you give me as many decimal points as your calculator spits out, unless I tell you to like round to 3 decimal places or 4 decimal places, which is often what I'll do, is ask you for a lot of decimal points. Why would I do that? To make sure you're using the maximum minimum commands and not just the trace function on your calculator, right? So makes it easier for me to test that you can use your calculator. That's the end of section 4. Wasn't this better once we got through section 2? Section 2 is just kind of a bugger. As far as the homework set goes, for Sunday, all I'm asking for is 1 through 4. That's it. Everything else that we've covered today will be part of next Sunday's homework set. So based on what we've done today, you guys could do 5 through 18. But that won't be due this Sunday, it'll be due the following Sunday.
Notre Dame. Before we end this day with a prayer, I just want to remind everyone that we will be celebrating Mass tomorrow as a community. If you have first period study hall, you should plan to arrive no later than 8:55 and go directly